notes about for liquids is colligative properties. When a solute is dissolved in a solvent, properties of that solvent are changed. These properties are known as colligative properties. So it doesn't matter what the solute is, when it gets dissolved in the solvent, there are things about that solvent, properties about that solvent, that are going to change because of the solute that's in there. And those properties that change, we call those colligative properties. They are dependent only on the number of particles of solute added, not on the identity of the solute. And what that means is that this is not a chemical interaction that we're talking about. This is a physical interaction that's going on between solute and solvent. So it is irregardless of the nature of the solute. It's only how many particles of solute you've got there. So these properties that change are the freezing point, the boiling point, the vapor pressure, and the osmotic pressure. Osmotic pressure we really talk about in biology more than anywhere else, not here in chemistry. So this means that the freezing point of a solvent will be lowered if you add solute to it. The boiling point of a solvent will be increased if you add solute. And the vapor pressure of a solvent will be decreased if you add solute to it. Okay, so boiling point elevation. So a real common, well, it might or might not be depending on if you cook, but what that means is that if you add solute to a solvent, you're going to increase the boiling point of that solvent. So, for instance, if you put sugar in water, you are going to change the boiling point of water to above 100 degrees Celsius. So, substances boil. A solvent will boil at a higher temperature. Okay, so it takes more energy to boil a solvent if there is solute there. If there's something dissolved in the solvent. And again, it does not matter what the nature of the solute is. Okay, so what about freezing point depression? Well, a solute added to a solvent will decrease the freezing point. And there are numerous examples of this. For instance, the ocean water does not freeze at 32 degrees Fahrenheit. Okay, why doesn't ocean water, the ocean water gets below 32 degrees Fahrenheit without freezing. Why doesn't it freeze? Because it has got a solute in there which prevents it from freezing at its normal temperature. And really, you guys, all the solute is doing is getting in the way, getting in between solvent molecules so that they can't lock up and form a solid matrix. Where else do we use this to our advantage? Now, here in Southern California, we really don't know this so much because we don't have to deal with it. But if you lay salt out on the roads, it will lower the freezing point of water so that at 32 degrees Fahrenheit or 0 degrees Celsius, water won't freeze on the roads. So you can lower the freezing point of water by adding solute to water. So in this case, salt. It's also important in ice cream making. And we will talk about ice cream making on the last day of school. We will utilize colligative properties to make ice cream in class. Okay, now let's do a problem. We will do this in lab. So freezing point depression and also boiling point elevation can be used to find the molar mass of a solute. So if you've got a solute with an unknown molar mass, you could theoretically use freezing point depression to figure that out. Alright, so what does this look like? Here is the formula. Change in T, so that's how much the freezing point has changed, is equal to I K sub F times M. Okay, what are all of these? Okay, M, we went over, is molality. So that's moles of solute over kilograms of solvent. K is the molal freezing depression constant for the solvent. So the mole freezing depression constant, and that is for the solvent. And like it says, you guys, it's a constant, so it's different for every solvent. And its units are degrees Celsius, kilograms per mole. So really it means how much does the temperature decrease for the kilogram of the solvent for every mole of solute added. And I is something called Van Hoff's constant. And for the problem that we're going to do here, Van Hoff's constant is going to be 1. And I will talk about Van Hoff's constant in class tomorrow. But for what we're doing right here, it's going to be 1. And really what it is, you guys, is this describes how many particles, when the solute dissolves, how many particles does it dissolve into? So if it's sugar, right, each sugar stays together as itself. So the Van Hoff constant is 1. If it's sodium chloride, you're going to get a sodium ion and a chloride ion, so the Van Hoff's constant will be 2. If it is calcium chloride, CaCl2, when it dissolves and dissociates, it's going to break up into a calcium and 2 chlorides. And so Van Hoff's constant will be 3. All right. for this one, you guys, it's a covalent solute, so it's going to stay together as just one. All right, a 7.85 gram sample of naphthalene, mothballs really, is dissolved in 301 grams of benzene. Oh, if this is benzene, and that's the solvent, do you think that solute is polar or non-polar? It's non-polar. Okay, the freezing point of the solution is 1.05 degrees Celsius below that of pure zine. Pure benzene. What is the molar mass of the naphthalene? Okay, so you're putting 7.85 grams of naphthalene into 301 grams of benzene. The freezing point is going to change by 1.05 degrees Celsius. We want to know what's the molar mass of the naphthalene, of the solute. And, oh, I wonder if you guys are going to be able to see that. The freezing point depression constant for the benzene is 5.12 degrees Celsius kilogram per mole. Our formula is delta T is equal to I K sub F M. Now, in this case, you guys, because the naphthalene is a covalent compound, it is not going to dissociate when it dissolves. So it's going to stay together as one particle. So this thing, in this purpose, what we're doing today, this number is just going to be 1. So you know what I'm going to do? I'm just going to take it out of the problem because it's 1. All right, now, we are going to rearrange this equation to look like this. We've got the molality of the solution equal to delta T divided by K sub F. Right? So all I've done is rearrange that equation. Okay. How much does our freezing point change by? It's going down by 1.05 degrees. And our freezing point depression constant for benzene is going to be 5.12 degrees Celsius per kilogram mole. Okay, and we know where this is going to go, right? This is going to end up going into the numerator. All right, so if we do this division, you guys, what do we end up getting? We end up getting 0.205. That is our number. And that is the molality of the solution. Okay? Meaning that we have 0.205, and that's equal to the molality of the solution. And what are our units for molality? It is moles of solute divided by kilograms of solvent, right? So, moles per kilogram, right? So this ends up being up there, and those cancel. So that means that, let's write this again. No, let's leave it just like it is. Okay. So we're looking for what? We're looking for the molar mass of the solute. Okay, and so we need to get moles alone. So we've got 0.205 is equal to the moles of solute divided by how many kilograms of solvent do we have? Well, we've got 301 grams, which is 0.301 kilograms of benzene, which is our solvent. So now what we're going to do is we're going to solve for moles of solute by multiplying both sides by 0.301. So that's going to leave us with 0.0617 moles of naphthalene. Okay, do you guys see how I did it? All I did was multiply both sides by 0.301. Okay, so now, great, we've solved for our moles of solute. 0.0617 moles of naphthalene, but we're looking for its molar mass. Okay, what are our units for molar mass? It's grams per mole, right? So how many grams of it do we have? So says our problem. We have 7.85 grams divided by 0.0617 moles. All right, you guys do the division, and I will check to see that you have the correct answer tomorrow for the molar mass of naphthalene using freezing point depression to find it. Okay, we're done.